Number 4 says the magnitude of thermal energy Q when a student produces 9.80 grams of iron 3 oxide is 47.2 kilojoules. The reaction that was performed is shown below. The production of iron 3 oxide is exothermic. Calculate the experimental delta H for the reaction. So problem A is asking us to find the delta H value for this entire reaction as a whole in kilojoules is what it's going to want. Now, the entire reaction produces 2 moles of iron 3 oxide. The student themselves only reacted and produced 9.8 grams of iron 3 oxide. And when they produced that 9.80 grams, they got a certain enthalpy change. So they got 47.2 kilojoules of energy, and it's exothermic, so a release of energy, for reacting just 9.80 grams. So we want to know the number of kilojoules for the entire reaction. So what we want to get to is the kilojoules for the production of 2 moles of Fe2O3. That's what we're trying to get to here. So we want to know how many kilojoules when we produce 2 moles of Fe2O3, when we do the whole reaction once. So first we need to figure out the kilojoules per mole for the reaction, and then we can multiply by that coefficient of 2 to get the kilojoules for the entire reaction. And so we have this number of kilojoules and we have a number of grams, but we don't want grams down here. What we actually want is moles. So I'm going to take that 9.8 grams, 9.80 grams of iron 3 oxide, Fe2O3, and we're going to convert that number of grams into a number of moles. So we know that 1 mole equals the molar mass. And if we add up the molar mass of iron 3 oxide, I got 159.7 grams per mole. So doing this calculation will give us the moles of Fe2O3. So when I calculate this out, I'm going to switch to a thinner pen, I got 0.061365 moles of Fe2O3. So now we can plug this in to the equation that we kind of wrote before. The number of kilojoules divided by the number of moles exactly will give us kilojoules per mole. So let's go ahead and do that. And I will do that over here. So negative 47.2 kilojoules divided by the number of moles, 0.061365 moles. So essentially what we're doing is we're simplifying this to get the number of kilojoules per 1 mole. So if we divide this out, we'll have the number of kilojoules per 1 mole. So let's go ahead and do that division. 47.2 divided by, I'm actually going to use the exact number of moles from my calculator. And when we do that, I got negative 769.167 kilojoules per 1 mole. That's our number of kilojoules per mole. Now, in this reaction, we want to know not the delta H in kilojoules per mole, we want to know the delta H for the entire reaction, which produces 2 moles of Fe2O3. So we just need to take that value in kilojoules per mole and cancel out the moles part of it. So to do that, I need moles to be on top, and I know that we have that many kilojoules per 1 mole of Fe2O3. I want to cancel out that moles of Fe2O3. So I'm just going to use my coefficient, the 2 moles of Fe2O3 that are in the reaction. So then, once I have my final answer, I will just have kilojoules for the entire reaction, because the moles of Fe2O3 will cancel out there. So we'll be left with just kilojoules in our final answer. So negative 769.167 times 2 gives me negative 1538.33 kilojoules. We should probably round to 3 significant figures here because that's what's given. So I'm going to round my final delta H value to negative 1540 kilojoules for the reaction. And that's our delta H for the reaction. So I can go ahead and put that next to my complete my thermochemical equation, negative 1540 kilojoules. So that was our experimental delta H value. The next part of the problem tells us that the theoretical enthalpy change for the reaction was supposed to be 1648 kilojoules per mole. So notice our experimental value is a little bit off from that. And part B asks us to find the percent error of the experiment. So I know percent error is equal to our theoretical minus our actual divided by our theoretical. So the difference in our theoretical value and our actual value divided by the theoretical value and then times 100 to get to a percent. So negative 1648 minus negative 1540, and it doesn't really matter if we have these negatives or we take the absolute value, divided by negative 1648. And it doesn't really matter if we have these negatives because there's negatives on both top and bottom, so I'm just going to go ahead and take those out. All we're interested in is the difference between the two values and the absolute value of that final answer. Alright, so the top of my negative 1648 minus 1540, so let's do that in my calculator. I did round my value to sig figs, and if you don't do that, you might get a slightly different answer. 108 divided by 1648, and then times 100 to convert to a percent. So when I did all that math, I got 6.5533, which is approximately 6.5%, or actually we should probably do 3 sig figs here, so 6.55% error. So not too bad there, a pretty good experiment overall, only about a 6.5% error.